In this example problem, we're going to use the rectangular stress block approach with factors proposed by Collins and Mitchell to find the moment in curvature when our top fiber strain is equal to negative 0.5 times 10 to the negative third. And we're also then going to develop a full moment curvature plot. We're going to do both of these, ignoring and including tension stiffening. So we'll start by finding our moment in curvature where we ignore our tension stiffening. And the first thing that we should do is draw our strain, stress, and force diagrams for our section. You can see we're going to assume we have a linear strain profile across the depth where the distance between the top fiber and our neutral axis is C, and the slope of our diagram is our curvature. You can see here we have our top fiber strain specified, and then we also need to find the strain in our pre-stressing and our bottom fiber strain. The rectangular stress block in general takes our non-linear strain stress profile for our concrete, and it approximates it as a rectangular stress distribution. So the area of this stress distribution and the centroid of this stress distribution are approximately equal to the area and the centroid of the actual stress distribution for our concrete. We have a beta 1 and an alpha 1 factor that we'll use, and these equations I'll show on the following slides. In terms of our steel stress, we only have our pre-stressing strands, so we'll need the stress in those pre-stressing strands, and then the force diagram will have the force from our pre-stressing strands and the force from our concrete component. And again, this is when we're ignoring tension stiffening to start. Now we're going to find our strains, our C, the depth of our neutral axis, and our curvature using a trial and error. We start by looking at what axial load we have applied. We have no axial load applied here, so our n is going to be equal to 0. Next, we would have to assume a top fiber strain in our concrete, and in this example, we're given this value. So at this point, now we can calculate our beta 1 value, and our beta 1 is going to be equal to 4 minus our top fiber strain, negative 0.5 times 10 to the negative third, divided by our strain at ultimate strength for our concrete, negative 2.25 times 10 to the negative third. And then all of this is divided by 6 minus 2 times the same value, same ratio. So negative 0.5 times 10 to the negative third, divided by negative 2.25 times 10 to the negative third. And this will give us a beta 1 equal to 0.68. Next, we can calculate our alpha 1 factor. So our alpha 1 is going to be 1 divided by our beta, which we found on the previous slide to be 0.68, times the ratio of our top fiber strain to our strain at ultimate, so negative 0.5 times 10 to the negative third, divided by negative 2.25 times 10 to the negative third, minus 1/3 times this ratio again, negative 0.5 times 10 to the negative third, divided by negative 2.25 times 10 to the negative third. And then this is squared. And this will give us an alpha 1 factor here of 0.303. We can use this alpha 1 and this beta 1 then to find our C. We'll start by guessing a value for C. We're going to guess a value of 7.28, and this is a good guess from a goal seek in Excel. So we'll start, and we can calculate our concrete force component. We'll have our alpha 1 0.303 times our beta 1 0.68 times F prime C 5 KSI times our C, 7.28, and times our B, 12 inches. So this will equal it'll equal 89.5. It's going to be in compression, so I'm going to make this a negative. Negative 89.5 kips. Next, we need to find the strain in our pre-stressing and are at the level of the pre-stressing. So we'll just use similar triangles and add in our locked-in strain differential here. So we'll get this strain to be equal to negative our top fiber strain times dp 20 inches minus our C, 7.28, divided by 7.28. And we'll get this value here to be, and then we add in our locked-in strain differential, so plus 6.0 times 10 to the negative third. And we'll get the strain in our pre-stressing to be 6.87 times 10 to the negative third. The stress in our pre-stressing, we're going to assume that we have a linear elastic response. So we have our stiffness for our pre-stressing, 28,500, times the strain in the pre-stressing, 7.87 times 10 to the negative third. And this will give us a stress in the pre-stressing of 195.9 KSI. To find our tension force then, we take this stress times our total pre-stressed area. So the total area of our pre-stressing strands is 0.458 square inches times the stress, 195.9 KSI, which gives us a value here of 89.9 kips. We can check our equilibrium expression then. Our compression component, our tension component, 89.9 kips, minus our minus our compression component, 89.5. And we can see this is about equal to 0. So we know that our C here checks. If we were doing this iteratively and we didn't get our total compression force equal to, or our total axial force equal to 0, then we would need to change our C until we got a value equal to 0. We can use our C to find the strain in our bottom fiber and our curvature using our strain diagram. Our strain in the bottom fiber is going to equal the top fiber strain divided by C, and then times this distance here, H minus C. The curvature is just going to equal the top fiber strain divided by C, assuming small angles. So we can find our top fiber strain, or our bottom fiber strain, sorry. So this will equal 0.5 times 10 to the negative third divided by our C, 7.28, times our overall height, 24 inches, minus 7.28. Will give us a strain here of 1.15 times 10 to the negative third. Our curvature is going to be equal to 0.5 times 10 to the negative third divided by our C, 7.28, which will give us a curvature here of 68.7 times 10 to the negative 6 radians per inch. Next, we can calculate our corresponding moment for this point. And we're going to sum our moments about the centroid of our section. So you can see our h over 2, and then the distance between the centroid of the force and h over 2, the centroid of our section, for both our concrete and tension forces. So plugging in our values, we can have our moment is equal to negative 89.9 times beta 1 over c, or sorry, beta 1c divided by 2, so 0.68 times 7.28 divided by 2, minus 24 over 2, or 12, plus our tension force 89.9 times 20 inches minus 12 inches. This will give us a moment here equal to 1,576 kip inches. So now we have our moment and we have our curvature at this point. We can now compare the values that we would get, or that we got using the rectangular stress block approach, to those that we would obtain using a layered section approach, in this case from Response 2000. You can see they're very comparable, and typically you'll get values within 5% of each other. So the next part of this example problem was to develop a full moment curvature plot, first ignoring tension stiffening. And I set this up in Excel, and you can see here some of the general inputs that I have in my Excel sheet that we need for all the calculations. On this slide, you can see the Excel sheet that I developed to develop a full moment curvature plot using the rectangular stress block approach from Collins and Mitchell. You can see that we vary the top fiber strain. So we select different values for this top fiber strain, and for each value of the top fiber strain, we calculate the beta 1 and alpha 1 values that accompany it. Next, we need to guess a C value, and we can calculate the compression force, the strain in the pre-stressing, the stress in the pre-stressing, the force in the pre-stressing, and then for that C, and add the force in the pre-stressing to the force in the steel, and see how close it is to 0. So what I did here is I used a goal seek for each row, where I set the objective being that this value here equals 0 by changing the C value. So you can see that for all of our values here, we have a total axial load in the column equal to 0. You can see then with that C, we can find the bottom fiber strain, we can find the curvature, and we can find the moment. And I give you all the different equations that I used in these different cells to develop this spreadsheet. The other thing that we can do is we can compare our beta 1 and our alpha 1 to what we would get with ACI. And you can see our beta 1 is about the same, or is the same as we would use in ACI. And the alpha 1 is a little higher using the Collins and Mitchell expressions than what we have in ACI. And I guess I highlighted the 0.003 because that's the strain in the top fiber that ACI assumes when the concrete crushes. We can plot our results from our rectangular stress block approach next to the layered section approach. So here you can see the blue is the rectangular stress block and the orange is our layered section. And you can see that the two are pretty close to each other. They're in general around 5% or within 5% of each other. So in general, the rectangular stress block approach is a reasonable way to estimate the behavior of a pre-stressed concrete member. In the next part of this problem, we're going to repeat problem 1 and problem 2, including tension stiffening. So so far we've ignored it, and now we're going to bring it in and see how it affects our results. The first thing that we need to do is figure out the area over which we can include tension stiffening. In general, we can include tension stiffening a distance 7.5 times the diameter of our strand away from the centroid of the strand. So on the top side, we need to measure a distance 7.5 dB. And on the bottom side, we'll have the minimum of 7.5 dB and h over d, which is the actual distance between the center of the strand and the bottom of the section. So here you can see that 7.5 dB is going to be 3.75 inches, and h minus dB is going to be 4 inches. So in this case, we're going to have 3.75 inches above and below the strand, making up the area over which we can apply tension stiffening. For flexural members, it's reasonable to assume that we'll use a stress of 0.5 times the tensile capacity of the concrete, and we'll use that in our tension stiffening region. So we have our area, 90 inches, we have our, or 90 square inches, we have our stress, 0.5 times the tensile strength of the concrete, so we can find our force. So 0.5 times the tensile strength of the concrete, 0.53 KSI, times 90 square inches, gives us a force here of 23.9 kips. So this is the additional force, the additional tension force that we need to include because of tension stiffening. So to find C, we need to go back to our equilibrium equation, and we need to add in our tension stiffening component. We have our compression component from our concrete, our tension component from our pre-stressing, and now the additional component from our tension stiffening in our concrete. And we have no externally applied load, so that this will be equal to 0. So I'm not going to show the specific details for this right here, but if we go through and solve for our C, we'll get a C equal to 8.95 inches from our equilibrium equation. With this value of C, we can find our moment. So we can add in our additional moment term for our tension stiffening component. And for this, we need to know the centroid of our tension stiffening block. So we have 7.5 dB above and below our strands. So the centroid of our tension stiffening component is going to be equal to the centroid of our strands. If h over d controlled, or h minus d controlled on the bottom side, then we would need to calculate the actual centroid of the tension stiffening block. But in this case, the tension stiffening block will have the same centroid as our strands, so 20 inches from the top. So we can calculate our moment, and our moment's going to be equal to negative 110.4 times 3.04 minus 12 plus our tension force in our pre-stressing, 86.6 minus 12, or sorry, times 20 minus 12, and then plus our 23.9 times 20 minus 12. So we'll get our moment here equal to 1,873 kip inches. We can find our curvature then by taking the top fiber strain, 0.5 times 10 to the negative third, divided by C, 8.95 inches, which will give us a curvature here of 55.9 times 10 to the negative 6 radians per inch. And then we can also find the strain in our bottom fiber by taking, again, our 0.5 times 10 to the negative third divided by C, 8.95, times 24 minus 8.95, which will give us a strain in the bottom fiber of 0.84 times 10 to the negative third. So here you can see we found, again, our moment and our curvature. So that's what the problem asks for, so those would be our answers here. We can compare, again, our rectangular stress block approach to our layered section approach using response, and you can see, again, we're similar, and we're within about 5% still, which will typically be true for the rectangular stress block approach. The next part of the problem is, again, we'll develop a full moment curvature plot, this time with tension stiffening. You can see here the inputs that I have for my spreadsheet that I'll show on the next slide. And you can see we have a few additional terms that we'll need, the diameter of our strands, and we have the area of our tension stiffening region and the centroid of our tension stiffening region that I include in the general properties. Shown on this slide is the spreadsheet that I developed to find our moment curvature plot using the rectangular stress block approach with tension stiffening. You can see, again, we're varying, or we can look at different points or different top fiber strains to get different moment curvature points. And for each row, again, we're going to use our goal seek to make sure that our total axial load is equal to 0 by changing C. You can see we have two additional columns in this table. One is our tension stiffening component for our concrete, and the last one is a capped moment capacity. So the capped moment capacity is essentially tension stiffening can't increase the ultimate capacity of a member. So we need to cap the capacity using the ultimate capacity without tension stiffening. So if you look back a couple slides ago, the maximum capacity of our section without tension stiffening is 2,136 kip inches. So this is the upper limit that we need to include in our tension stiffening plot. You can see I lay out again the different equations I use in all the columns, so you should be able to set up a similar spreadsheet on your own. The other thing to highlight is when our compression, or when our neutral axis falls down below or near our pre-stressing strands, the concrete there will be in compression. So we don't want to include tension stiffening when our concrete in that region is in compression. It would be like double counting your concrete. So I manually set those equal to 0 if the compression block falls in the tension stiffening region. Here we have the points from our previous slide plotted against the points from a layered section approach. You can see our points from a rectangular stress block next to the points from the layered section approach. And again, we're within about 5%, or the points are within 5% of each other. So you can see that we can reasonably estimate the behavior of our section with and without tension stiffening using the rectangular stress block approach with factors proposed by Collins and Mitchell. You can see down here the effect of tension stiffening. So our with and without tension stiffening values. And you can see it doesn't increase the overall moment capacity, but it does increase the capacity at different points, or it does increase the moment at lower curvature values. So it essentially stiffens, it creates a stiffer behavior because we're including the stiffening effects of our concrete and tension around our strands. So you can see the general effects of tension stiffening right there in this plot. That concludes this example.